Okay, class, welcome to lecture 7. Today we are talking about some more probability stuff. Specifically, we're going to talk about multiplication and complement rules. Okay, so we will introduce this stuff with a question, which is different than the types of probability questions we have looked at so far. Okay, so here it is. What's the probability that if you roll a dice, you roll a 5 with a dice, and then so you do two things. You roll a 5 with a dice, and then you draw I don't know, a spade from a deck. So what's going on with this question? So in the other video, we were always just doing like one thing at a time. So like, what's the probability you roll 5? Or a different question would be, what's the probability you draw a spade? And then we did addition rules, which came from asking what happens if you do this or that. But now an and is between the two events. So let's sort of pick this apart. Okay, so here, if I want to think about it using this fancy notation, I call events E, then I'll call this one E1, roll a 5, and E2, draw a spade. So of course, from a deck, I'm just shortening it. I'm rolling a 5 with the dice. So here, these are not, to use the fancy language, part of the same sample space. So the idea is that they're unrelated to each other. Rolling a 5 is doing one type of thing, one type of action, and drawing a spade is another type of action, either rolling a dice or drawing a card, two different actions. So what this is saying then is a couple things, but first of all, these two events I can say are not disjoint. So that's what we talked about last time. Disjoint events, what were those? Those were events that could not happen at the same time because they were coming from the same action, like rolling a dice. I can't roll a 3 and a 5 with the same roll of the dice. But here I'm doing two different things, one after another. So I could do them both. I could certainly roll a 5, and then right after that, I draw a spade from the deck. That's perfectly fine. So they're definitely not disjoint. Okay, so now, in fact, not only are they not disjoint, we are asking when they do happen together. We're asking how likely it is that they both happen. So very opposite of being disjoint. Not only do they happen at the same time, can they happen at the same time? I want to know how likely that is that they do happen. But so instead of being disjoint, there's another fancy word that describes their relationship, which is that they do not impact each other. So if I roll a 5 and then I don't draw a spade, there's no reason that one has to happen because the other happens. They're completely separate from each other. And they could happen at the same time, they could not, but they don't affect each other. So they do not impact each other. And what that is called, or what that means, is that they are independent events. Independent. So this is the other fancy word. So please do not get it mixed up with disjoint. Disjoint means that they cannot happen at the same time, like rolling a 5 and rolling a 3 at the same time with one dice. Those are disjoint. Versus independent, they don't affect each other. Rolling 5 and drawing a spade is independent because doing one doesn't affect the other. Okay, so now let's answer this question. So because we don't know how to do it, we're going to use the definition of how we think about probability. So what do we know? How do we deal with probability? Well, we use this big fancy notation first of all. So P of, and then we write the event down, roll a 5, and draw a spade. What should that equal? Well, we learned that the probability of an event is just the number of ways that that thing could happen versus the number of things that could happen total. So since I am rolling a 5 and drawing a spade, on the top here should be the number of ways that that can happen. So number of ways to draw roll a 5 first. To roll a 5 and draw a spade. And then what would be on the bottom? Well, what can happen in total? Well, it just comes from my 2 actions. So I'm rolling a dice and I'm drawing a card. So the total things that could happen are the number of ways to just draw any card, or roll any number, roll a die, and just draw any card. So these are the 2 numbers that'll tell us the probability if I can figure them out. All right, so we got to learn how to do that. So again, probability is just fancy counting. So how do we count these things? One useful tool is to visualize this with something called a tree diagram. And so here's how it'll work. So we're going to think of these 2 events as, well, because they are 2 events, E1 and E2. So let's just focus on one at a time. So the first event is it's rolling a 5, and it comes from the action of rolling a die. So let's think about what are possible outcomes of doing the first thing, which is rolling a die. Dice, I still don't know. I can just draw them. I can get a 1, a 2, a 3, a 4, a 5, or a 6. Those are the possible outcomes to help me visualize what's going on. And then the idea is, what happens if I just get the first one? So let's think about, suppose I roll a 1. So I rolled a 1, and then after, what can happen? I draw a card, but how many cards can I choose from? 52, because that's how many are in a deck. So the idea is that we draw 52, this is why it's called a tree diagram. We draw 52 branches coming out of 1. And this tells us all the different outcomes that could happen if I rolled a 1 first. Of course, I'm not going to actually draw 51 things because it's too many, but I can just sort of get the idea across like that. The idea is that there are 52 choices, 1 for each card. So what this represents is all the possibilities that could happen if I happen to roll a 1 first and then I draw a card. So then we say, okay, but I could also have rolled a 2 first. So I'll draw another tree or another smaller branch, a bigger branch with lots of branches coming out of it for a 2. Because what could happen is I could roll a 2 first, and then I could have 52 more choices. Well, 52 of the same choices as before, 1 for each card. And you could keep doing this for each number that you could roll first. So then there would be a 3 with 52 more choices, and a 4 with 52 more, and a 5 with 52 more, and a 6 with 52 more. So then this is actually telling us the total number of possibilities, this little picture here. The number of total branches is the total number of possibilities. Okay, so this creates the tree diagram. And this is what lets us visualize the total number of possibilities. Which is the bottom number in the fraction. So what is it? Well, the idea is that there's 52 branches for the 1. There's another 52 branches for the 2, another for the 3, oops, and so on for all 6 possibilities that I could have started with. But a faster way of saying that is just 6 times 52. And so this is the bottom number in our little probability calculation here. Okay, so that's the total number of ways to roll a die and draw a card. The idea being because really, secretly, it's because there's 6 ways to roll a die. And then for each one of those, you could do 52 different cards. So you end up multiplying 6 times 52. Okay, so now how do we get the top number? So what about the number of ways to roll a 5 and draw a spade? It's going to be very similar. So I can roll a 5 to start, and then how many different spades can I choose from after that? Well, there's 13 of each suit. So in total, this is the end of the tree diagram for this situation. I just have 1 branch to start here, and then out of that branch, I have 13 branches coming out for a total of 13 branches. And you can think about it as 1 times 13. So there's 13 ways to do this. So the 1 is sort of stuck there as a 1 because there's only one way to roll a 5. You just do it. You just roll a 5 with a dice. But there's 13 different spades you could draw out of the deck. So that's why we got times 13. But the 1 is just a 1. Okay, so then what's the answer to the original question? So the probability of rolling a 5 and drawing a spade. Now I have my top number as 13 and my bottom number as 6 times 52. And you can use a calculator if you want to reduce this. It'll be 1 over 24. But I like to leave it like this to see where the numbers came from. Okay. So let's use this idea to do a couple more just for extra practice. So let's see if we can establish a pattern. Let's find the probability that you roll an even number with a die and then draw a heart. It's going to be very similar. So we'll just do it the same way. So it's got to be the number of ways to do this thing to roll an even with a die, and draw a heart from a deck, divided by the total number of ways to roll a die. This is the same as before on the bottom because I'm doing the same 2 things. I'm rolling a die and then I'm drawing a card. So this is still going to be 6 times 52 because there's 6 ways to roll a die first, and then there's 52 ways to draw a card. But now on the top, we can draw a new tree picture. So I have to draw one branch for each thing that could happen first. So I have to roll an even number first, and then I have to draw a heart. So first I'm going to draw a branch for each way to roll an even. Well, I can roll a 2, a 4, or a 6. And then how many ways are there to draw a heart each time for each one of those possibilities? Well, there's 13 of each suit, so there's 13 branches coming out of each of these possibilities. So the idea is that there are 3 ways to do the first thing. I could roll 2, 4, 6, and out of each of those branches comes 13 more branches for a total of 3 times 13 possibilities. So that's going to be the number on the top. But I'm going to be very sneaky here. I'm going to leave it like this to see if you notice the pattern. So you might see it at this point. What if I just asked these 2 questions separately? What if I just said, what's the probability to roll an even? Well, there's 2, 4, 6 are the evens. So there's 3 ways to do that. And there's 6 total dice rolls. What's the probability of drawing a heart? Well, there's 13 hearts out of 52 cards. Oh, but isn't that what these 2 numbers are here? Yes, it is. And luckily, multiplication I can break up like this. This is exactly the same as this. And now I'm going to translate it back to words to see what this is really saying. This is really saying that to calculate this probability of rolling an even and then drawing, the keyword is and here, and then drawing a heart, all I have to do is calculate each probability separately and then multiply them together. Because this is really, on the top, this 3 is really the number of ways to roll a 3 divided by the number of ways, sorry, not roll a 3, roll an even, divided by the number of ways just to roll any dice number, to roll a die, times number of ways to draw a heart, divided by number of ways to just draw a card. And what are these 2 things? These are just probabilities. This is really the probability of rolling an even times probability of drawing a heart. So this is the pattern we're trying to establish, that if I want to know the probability of 2 things happening, and the key is that they're independent, then I can just multiply the 2 probabilities together. Okay, so that's the big picture idea. So let's summarize that. So this always works for independent events. Meaning 2 events that don't affect each other. The answer is that you can just do the probability of the first event and the second event happening by just multiplying the 2 probabilities. But this only works when they are independent. If they're not independent, then it won't work. Because these numbers affect each other, so you can't just separate them like this. Okay, so let's do some more examples and following other things. So for example, if I want to find the probability of, if I flip 3 coins and I get 3 heads in a row, 3 heads and 3 coin flips. Well, the idea is that each flip is independent. Each flip is independent of the others. If I flip a coin and it's heads, then when I flip it again the second time, it doesn't matter that the first one was heads. It doesn't affect what the second one will be. So each flip is independent of the others. So what that means is, if I want to find the probability of flipping 3 heads by flipping 3 coins, then I can just think of it as I flip and I get a heads, and then I multiply and I flip and I get a heads again. And again. So, and now I do know the probability of each one of these. What's the probability of flipping a head with just 1 coin flip? That's just 1, because there's only 1 way to get heads out of 2 possibilities, heads or tails. And so each of these are 1/2. And you get 1/8. Cool. And you can also think about the coin flipping using the tree diagrams, and you'll get the same answer. So let's do that just for practice. So the idea here is each event is a branch coming out of the previous branches. So the idea is that there are 2 possible outcomes. To start, I can either get heads or tails. So that's how many branches I start with. And then each outcome has 2 branches coming out of it for the next event. And that's because if I get a heads first, my next thing that I could do is I could get a heads or tails after getting heads first. Because 2 things can happen after the first outcome. So you draw 2 branches, heads and tails. So because it's not 52, I'm actually drawing the right number, which is 2, and I'm labeling them. But for the card one, there was 52 branches, so I didn't want to label all of them. I didn't even draw 52. I just labeled it as 52. Okay, so if I got a tails on my first flip, then what could happen next? Again, I could either get heads or tails after that. Okay, so now what happens if I got heads? Well, that's saying that this is what happened. And then on my third coin flip, I could have 2 more branches coming out of that for what could happen afterwards. So after I get 2 heads, I could get another heads or I could get a tails. And then that's how we're going to get all the branches here. So the same idea applies to the rest. You just get 2 more branches out of each. And then you'll notice that in the end, there's 8 total paths. Or you could just think of them as 8 total branches from beginning to end. 1, 2, 3, 4, 5, 6, 7, 8. Because what this is doing is telling us the bottom number in the probability, if I think about it in the original way, which is so number of ways to flip 3 coins, that's going to be what's on the bottom. So that's going to be 8. And then what's on the top is the number of ways to flip 3 heads. Well, how many ways can I do that? The only way is if I happen to get heads. The other paths don't have 3 heads in a row. So there's only one way to do that. 3 heads in a row. So that's going to tell us that this top number is 1. There's only one way to do that. So Either way, you get 1/8, which is good because math is consistent. Okay, so the multiplication rule is really just doing this tree diagram business faster so you don't have to draw pictures constantly. That's really what it comes down to. Okay, so the multiplication rule. Just does these tree diagrams, but faster. Okay, so now let's do an example where we just sort of apply the rule as fast as possible to see how it's not so bad. So for example, if I want to find the probability of, let's see, I'll flip a tail with a coin, and then I will draw a face card from a deck, and then I will roll a 3 from a dice. So I'm doing 3 events now. So because they're all independent of each other, flipping a coin does not affect drawing a card, does not affect rolling a dice. I can use this multiplication rule. So each event is independent of the others. So I can just break it up into probability of doing each one. Flip a tail times probability of draw a face card times rolling a 3. So what's the probability of flipping a tail in a coin toss is 1 out of 2. Drawing a face card, well, I got to count that. Let's see. So there's 4 face cards for each suit, so 16. Because there's the jack, the queen, the king, and the ace. Okay. So there's 16 of those out of 52 cards. And there is just a single 3 out of 6 numbers on a dice. So this is the answer. And of course, you could multiply it out if you want, but it looks better like this because you can see where all the pieces are coming from. And if you drew a tree diagram for this, it would be the same. You would get the same answer. So you would draw heads and tails because you're flipping a coin. Then you would draw 52 branches for your drawing a card. And then out of each of those 52 branches, you would draw 6 more branches. But I don't want to do that because it's going to take forever. And then the total number of branches will be 2 times 52 times 6, which is, again, the bottom number of the probability, 2 times 52 times 6. And then the number of branches that actually have a tail, so it would have to be this one, and a face card and a 3, there would be 16 of those branches if you actually went and drew the entire thing. Okay, well, we're not going to do that because it's a big giant tree. All right, so one more rule, and that's it. So the next and final rule is called the complement rule. It's also the most intuitive rule. Sort of makes sense once you think about it intuitively. So the idea is this. If the probability of event E happening or occurring, however you want to say it, is some number, P of E that you call it. So like you could just pretend for now that this is some event specifically, and this is specifically some number, maybe like 1/3. Okay. Then what's the probability of E not happening? Well, everything either happens or it doesn't. So that's what we're going to use. So the probability of E not happening is, well, because probabilities have to add up to 100%, it's 1 minus the probability of E happening, because it either happens or it doesn't. And because of this phrase here, the total probability of E happening or E not happening has to add up to 1. So what that means is that if the probability of E happening is a third, for example, then the probability of E not happening better be 2/3 so that they can add up to 1. And how did I get 2/3? Well, I really am doing 1 minus 1/3. Okay, so that's the idea. Things either happen or they don't. So if you know the probability of something happening, then the probability that it's not happening must be 1 minus that number. All right, so we can use this in practice real quick. So what's the probability of not rolling the 3 with a die? Well, it better be the probability, 1 minus the probability of that event happening. So as long as I know the probability of it happening, I could figure out the probability of it not happening. So the probability of rolling a 3 is 1 out of 6. So that means the probability of not rolling a 3 is 1 minus 1 over 6, which would be 5 over 6. Okay, so this trick is useful for more annoying problems like the following. Useful for things like this. So what's the probability of drawing in a deck an ace or a 2 or a 3 or a 4 or a 5 or all the way down to queen? So if I wanted to calculate this manually, I would have to count up, well, it's going to be out of 52, which is 52 cards. But I have to think about how many aces there are, how many 2s there are, how many 3s, 4s, 5s, all the cards except kings. So I could think of it as not a king. Instead, because that's really what this is saying. This is saying all the cards except a king. So as long as I know the number of kings, I can figure this out more easily. So that's the idea. So instead of counting this, we're going to calculate something a lot easier. We're going to calculate the probability of not drawing these things, which is the same as the probability of drawing a king. And so what's that? Well, there's only 4 kings. I only have to count up to 4. I don't have to count all these other things. So that means that this original question is just going to be 1 minus that. So then the probability of drawing one of these cards, any other card that's not a king, is just going to be 1 minus drawing a king, which is a lot easier to do. Okay. So lots of examples like this will be on the lecture problems. But that's it for this time. So see you later.